Okay, in this demonstration we're going to explore good old rise over run, and on the GeoGebra sketch on the left side I have a green line which is called a secant, and the secant is between the 2 points on this function. Now this is any general function f, so we have a function f of x. The red lines clearly can see there are the rise and the run. Now, as the 2 points get closer together, what happens to the length of the run? Well, as you can see, the run and the rise are getting smaller and smaller and smaller. But of course, rise over run is a little bit tricky, because if the run is 0, we have division by 0, which we do not want. That doesn't compute at all. So what we're going to look at is, in demonstration here, the green secant, as the 2 points get closer together, the green line becomes the tangent at the point given. So we now have a gradient of a tangent. Now that is only going to be true when there's a run. If there's no run, there is no tangent, because we cannot divide by 0. So just before the run disappears, just before the length of the line gets to 0, we're going to say stop, and we're going to mark that, and that will be our tangent. Okay, so that's the general idea. Now, coming back onto the right side, we know from previous work that we're looking at y2 minus y1 over x2 minus x1. So we have 4 values, 2 y values and 2 x values. So at the moment we've got the gradient of the secant is going to be, now let's have a look at the 2 y values. You can see on the sketch that we've got the larger y value is that one. So if I take those 2 away, that's the value of the rise. Looking along the x-axis, we've got this value for x, which is x plus h, and we're going to take away the other one, and that will give us the distance, the length if you like, of the run. Straight away you can see that in the denominator the x's cancel out. So as we move the 2 points closer, h, the value of the run, h, gets smaller and smaller and smaller. Just before it disappears, just before it comes 0, that is the gradient of the tangent. So in other words, the gradient of the tangent is going to look pretty much the same. But what we're looking at is the limit when h tends to 0. In other words, it's tending towards 0. The run is getting smaller and smaller and smaller and smaller, but it's not actually going to equal 0. Just before it does equal 0, that's what we're looking for. So what we end up with is this quite complicated looking expression here, or formula, or rule, which is actually rise over run. It's as simple as that. We call this fancy looking thing the derivative function. And that's all we need at the moment.